Hey Ramblers! This video covers chapter 7.1 in our textbook and deals again with integration by substitution. But it's going to be part B of the first video because we're going to extend the substitution process to definite integrals. In other words, can we still use substitution when we have limits? And how do we do it? The important thing I want you to take away from this video is that you can use substitution, but that there are two methods, and you just have to be clear on which method you want to use. You don't really need to know both of them. You just need to have one that works for you and be clear on how to use it so that you don't confuse it with the other method. Okay, Ramblers, thanks for watching. Take good notes, and I hope this helps.
Before we get into the main topic of this video, I wanted to touch briefly on what we did in the last video. Now, the last video dealt with using substitution as a method for integrating indefinite integrals. So in other words, there were no limits to deal with. And as you may recall, we looked for a function that was a composite function where the inside function, in this case g of x, had its derivative, g prime, also in the integrand. When we did that, that meant that the integrand was obviously that derivative had come about by the application of the chain rule, and so we were trying to undo the chain rule. The method, of course, was to set the inside function, g of x, give it a new name, w. And the derivative of w we called dw, and that equaled g prime of x dx. All of this allowed me to make a substitution into the integral so that I had f prime of w dw. Now, that's easier to integrate, and when you do, you get f of w plus c. Of course, we had to substitute back in, so we ended up with f of g of x plus c. Now, obviously, when you take the derivative of this composite function, you will get what we started with. The derivative of that would equal f prime of g of x times the derivative of the inside function, g prime of x. So substitution works. Well, what's this video about then? There are going to be two methods when we deal with using definite integrals. Now, you can recognize a definite integral because it has limits. And so when we deal with these limits, we have to be very careful of what variable we have the limits stated in. Please get that in your notes. That is really what we're being careful to avoid, is any confusion that comes about sometimes when you use substitution. So I'm going to have two different methods. I'm going to use different backgrounds to really help you just differentiate between the two of them. And it's just important that you choose one method. All right, that's all you need to know, but just know enough not to confuse it with the other one. Okay, so the first method involves changing the limits into the new variable, and the other method keeps the limits in terms of the original variable. So let's see which one you like better. Okay, the first method is going to involve changing the limits of integration in terms of the new variable. It's easiest if I show you an example. So when I take a look at this definite integral, you see that I have limits, and I see a composite function. So natural log is inside the cubing function, and its derivative 1 over x, and I can imagine a 1 in the numerator, over x, shows that I have the inside function and its derivative in the same integrand. So it's a perfect candidate for substitution. So why don't we use that? Well, w is going to equal the natural log of x, and then dw will equal 1 over x dx. So when I rewrite that, I have my integral of w cubed and then the dw will represent the x and the dx. Now what do I do with my limits? And here's where it starts to get a little tricky. If I write my limit in as 1 to e, that's confusing because I'm no longer dealing with natural log. This is an integral that deals with w cubed. That's very different than an integral that dealt with natural log from 1 to e. So the proper thing to do is to change the variables into, change the limits into the new variable. So back in this first step, we should say w of e will equal the natural log of e, which of course equals 1. And w of 1 will equal the natural log of 1, which equals 0. So when I rewrite my integrand, I'm not going to have limits of e and 1. I'm going to have limits of 1 and 0. So that when I take my definite integral and I find the antiderivative, I'll get w to the 4th over 4, evaluated not from 1 to e, but from 0 to 1. Now I just plug in 1 and 0, so I'll have w to the 4th, which in this case is 1 to the 4th over 4, minus 0 to the 4th over 4, which equals 1/4. And so that's my final answer. Notice, I never resubstitute in this method, and that's what makes it pretty attractive. It seems like it saves a lot of work. So let's try another example, just showing you how it works again, so that you're more comfortable with it. Okay, once again, we'll take a look at a composite function. I have x squared inside the e function, and its derivative, x, is there. The derivative should be 2x, but it's only off by a constant. So this is a pretty good candidate for substitution. Let's try it. Well, w is going to equal x squared. dw will equal 2x dx, and since I don't have a 2 in my original integrand, I have to divide both sides by 2, and that covers everything. So because I'm using substitution, and I'm switching from a variable of x to a variable of w, I need to rewrite my limits in terms of the new variable. So w of 3 equals 3 squared, and w of 2 equals 2 squared. So I can now rewrite my integral in terms of the new variable w with the appropriate limits. So my limits are now, instead of from 2 to 3, they're from 4 to 9, and I have an integrand of e to the w dw. Now when I integrate that, I'm going to get e to the w, of course, evaluated from 9 to 4, which equals e to the 9th minus e to the 4th. And that's your final answer. Once again, notice I never had to substitute back into x in order to get my final answer. All right, now let's take a look at the other method to make sure it's really clear to you. The second method requires that we keep the limits in terms of the original variable and then resubstitute at the end. So let's take a look at how that works. I'm going to take the same example used before. So once again, the substitution is the same. So our inside function is still the natural log of x, and so our derivative will be 1 over x dx. So when I rewrite this, I will have w cubed dw. Now what's different is the limits here. Instead of writing or changing the limits in terms of into w, I'm going to keep them as x equals e and x equals 1. You have to write x equals because the variable in the integrand is w, but the limits are in terms of x. So now we're going to continue with the integration just as we always have. You're going to get w to the 4th over 4 evaluated at, once again, we have to write x equals e and x equals 1. You can't plug e and 1 into this function, into this expression, because it's supposed to be in terms of w. So now we have to resubstitute. So let's bring it over here. And since w equaled the natural log of x, I will resubstitute and have the natural log of x over 4 raised to the 4th, evaluated at e to 1. Or I'm sorry, 1 to e. So now I'll take the natural log of e to the 4th over 4 minus the natural log of 1 over 4. Of course, the natural log of e is just 1, so we get 1/4 minus 0 over 4. So you can see we get the same answer. It's just different work. Let's take a look at another example, and then we'll wrap things up. Okay, let's take a look at a second example, just to see if things can really sink in. Once again, good candidate for substitution, since we see a composite function where the derivative of the inside function is also present in the integrand, and it's only off by a constant. So we make w equal to x squared, and then dw will equal x dx. Of course, this should have been 2x, so we'll have to divide by 2. And now we'll rewrite this expression with the substitution. I see it's e to the w dw, and then my limits, once again, I'll have to write x equals 3 and x equals 2. So now I will do my substitute, or I will do my integration. E to the w evaluated from 2 to 3. But again, I have to write x equals 2 and x equals 3. It's really easy to forget to do that. And then you plug in the wrong thing at the end if you're not careful. So now I have to substitute back. So e to the w had equaled x squared, so it's e to the x squared. Now I can evaluate this expression. E to the 3 squared minus e to the 2 squared gives me e to the 9th minus e to the 4th, and that was the same answer we got before. So Ramblers, take your pick, method 1 or method 2. Method 1 involves converting your limits into the new w variable, but there's no resubstitution step. On the other hand, you could keep writing x equals, or your original variable equals, but then you have to also resubstitute at the end. Choice is yours. Okay, Ramblers, we'll do some work on this tomorrow in class. Thanks for watching.